Hi, thanks a lot for coming. Scaling ACID is the headline of the talk. So before I start, maybe a question. Has anybody here run into this situation in the past where he felt like, okay, ACID would be really nice now? Like, all right, thanks. So it's quite some people understand immediately why ACID, especially in a time when we hear a lot about NoSQL and everybody probably has tried some NoSQL, then all of a sudden can be something that we were used to in the past, but now it's not a given anymore. So that whole project that I'm talking about, Erlvolt, is also on GitHub. You could check it out and play around with it on the side while I'm introducing the concepts that are behind it. And I want to dedicate the talk to Gustav, who is not here now, who's a great colleague and would love to be here, I guess. So for me, the discovery of VoltDB actually was happening on a quest to looking for the perfect game server. I had worked on a pretty audacious MMO project. We had successfully implemented a lot of interesting stuff and had Java as a backend. And that Java server was talking to a very vanilla MySQL setup, extended with some memcached caching operation that, if you thought through it, was just not sane. It kind of worked. It kind of saved the day. But after that experience, I went on a research to find out what could be a proper solution to the stuff that we had encountered. And yeah, that's, as you already heard, was the beginning of that journey that I'm now in the moment doing for the 4th year, I'm thinking. I'm also working as a lead software engineer at SumUp, where we're doing a payment stack for credit card payment and using Erlang there for another type of high security, high reliability situation. And to understand how to create the driver for VoltDB for Erlang, I also became the maintainer of eMySQL for a certain time until somebody much better than me took over. And just to be very clear, Erlvolt is simply the name for the native Erlang VoltDB driver that I programmed throughout the last 3 years, and it's open source. It's part of the official distribution of VoltDB, and it's also used in production successfully at companies that are, what I'm hearing, quite happy about it. In my view, VoltDB and Erlang, who I kind of found independently of each other, are a scale dream team. And I would like to try to explain how they are special, how VoltDB is special when working together with Erlang. How does it actually look? How does the source look? And answer the question if it is for you and meets the use cases that you might have. So talking about VoltDB, it started with a great idea, certainly. And part of Erlvolt was programmed on a tropical island. At least that was the plan. And some source codes also actually were created there. And that's actually not the Crimea, although it looks like it. But I think it also looks very much like Treasure Island. And in the end, we even discovered it was a pirate island, actually. Of course, there are many other things you could do. You can hike, you can bath. It's pretty warm. It's pretty sunny. And at some point, I started to create this cartoon, which summed up my dilemma, that tropical island. You can do that on cmx.io, and I'm sure you all know xkcd. And I sent that over to the VoltDB guys, and especially the CTO, Ryan. He just loved it, because VoltDB, of course, was also founded on a great idea. And when they started out, it was probably a given that it should be a database that is doing the best that's possible with horizontal partitioning. And that was just said out at the start. And then they had something there that was single-thread execution that for Erlang, we all know very well how to work with that, just working on the fact that a single thread cannot raise itself. And on top of that, they had a very beautiful idea about a kind of rhythmic distribution of tasks around the nodes so that they would have a kind of heartbeat that would make sure that the individual threads that are working on different nodes on the horizontally partitioned tables would not step on each other's toes. The man who drove that invention was Mike Stonebreaker, and he's a very outspoken guy. He's in the database business since a very long time. He's the guy who was behind Ingress. He also created PostgreSQL. And at some point he said it's time for a complete rewrite, and one size doesn't fit all anymore. So what resulted from that were Vertica and VoltDB. And Vertica is a vertically partitioned database, and VoltDB is a horizontally partitioned database. There's a very good paper that I can only recommend to read, and the link is down there. It's called hstore.pdf. That's the research where it originally came from. So what is VoltDB? In a nutshell, I'd like to describe it as Redis plus SQL plus scaling. Sorry. And the beauty of it is it's in memory, and that means it's incredibly fast. But it keeps SQL, and it even keeps ACID, which can be very important. And because of the way that it uses a cluster, of course it has the expectable ways of replication. And meanwhile, in version 4, it also has ACID elasticity, so you can add additional power while it's running. If you're online, you can actually try Erlvolt out pretty fast. This is how you could just clone VoltDB, clone Erlvolt, compile them, and let them run. And I also created a gist that's down there, the URL, if you want to note that, where you can read the instruction on how to play around while I'm going into details. What you would do if you, what you would see if you tried that out is simply at a certain point VoltDB starts, then you would see a benchmark that I will explain a little more in detail later, executed, and in the end you would see your local results for what VoltDB can do on your computer using it as one node. So what are the use cases for VoltDB? From a business perspective, VoltDB is positioned where big data, like really big data, has to be queried for answers as fast as possible. Where data comes in and you want to be able to say within seconds what the current status is. Of course, this is a way to avoid MySQL clusters that are just not sane, or other constructs that might, for example, be great to have map-reduced stuff, but isn't as fast and isn't from the architecture as well suited. There is also the strategic flexibility that comes with VoltDB because it is not, in a way, fixed in the architecture like you have it if you are deciding for a NoSQL setup, where you have to make very far-reaching decisions very early on. Now, from the production perspective, it mainly takes the pain out of scaling, and that's really what's happening. It's scaling incredibly well. You have the speed of in-memory, which is 80 times faster than, for example, MySQL, and you have the good parts of SQL still, although it has a lot of features that you would usually find in NoSQLs. Where they're positioning themselves, and this is a graphic from VoltDB, is at that spot where the data is really fresh. The idea here with this graph is from the left to the right, you have increased age of data. And from the bottom to the top, the value of the data increases. So if data comes in, you can have situations in this chart where you say, okay, the fresher the data is and the faster I can make an analysis of the data, the higher the value. And that makes Vault interesting for situations where you have necessity to have answers within milliseconds or hundreds of seconds. And it's not necessarily the right choice if you have minutes or hours to have the results of your statistics. Then you might want to use other tools. So that is the complete landscape, where you can see Hadoop on the right side. You see traditional RDBMS in the middle at the bottom. And you see VoltDB there in the corner where velocity and high throughput would be at home. So the use case is definitely high throughput. It's fast operations on high-value data. And it's also resilience to failure when using very normal commodity hardware. VoltDB itself, and that's also a parallel to Erlang maybe here, VoltDB itself is a 100% dictatorial open source project, which is driven by VoltDB Inc. And that's also good, I mean, because you have the chance to have high value support. It is really moving forward. There are no gaps in development because somebody has no time or so. And it is absolutely made for OLTP. Like we just said, online transactions, fast and cheap writes, high throughput, that's where it's at home. If you look at CAP and or getting oriented about where it's in that category, it's probably on the CA side, although Stonebreaker is arguing that CAP is maybe misleading here and VoltDB is really all three. If you have other advantages that I'll come to, there's also one thing that VoltDB, in my view, is even more SQL than SQL. Because it's cleaner, it allows more cleanliness and separation of the data compared to if you, for example, use MySQL. The parallels between Erlang and VoltDB I find very interesting because they're coming from a very similar corner, so to say. They're both made for a concrete need. They're both made for distribution. They're made for multi-core. And they are truly different approaches to what has been there before. They are based on hardware parallelism. They're not like many other products now stumbling into an environment where all of a sudden you have hardware that is not getting faster per CPU anymore, but just gets more and more cores. And as a result, they're really substantial improvements above what other products can give you. What is also maybe interesting is that VoltDB is not so well known, but people that I talk to that actually have the problem that VoltDB is good for solving usually know it. And that's very similar to Erlang, where I can still run into people who are fresh from the university who never heard about Erlang. But those who are in fact working on problems that are close to the heart of Erlang are usually knowing it. VoltDB has quite a lot of customers, meanwhile, also in the gaming sector, as I said. And I would like to go into the individual features. Again, in memory, we had that VoltDB does deliver the same speed in a way that in-memory databases like Redis can deliver, but at the same time, it's fully replicated, it's fully disk persistent. Who knows about the details knows that in the end, you even have to have the right hardware controller, the hard disk controller, to be really fully disk persistent. Since the first version, VoltDB has improved a lot on that angle. Talking about SQL, maybe not anymore now, but 2 years ago or so, SQL started to be a real dirty word. And the thing that has to be kept in mind is that SQL is maybe flawed in how its syntax is, but it's essentially it's math. And whatever you use to formulate certain relationships in data, what it boils down to semantically is always going to be very close to what SQL offers you. What I started to mention before, that VoltDB is actually more SQL than SQL sometimes, that's because if you optimize stuff, sometimes you would, for example, have an array that you know it's always going to be in the joins, so I can make it a dictionary and have it in memory, and it's going to be so much faster, and I don't have to put it in all the queries. And then you end up having a faster application, but it's also harder to maintain, because then when the data structure changes, then you have to change it in two areas. Somebody else who needs to learn it has to understand about the hack that you put into your application. And with VoltDB, what they are doing is so fast at any rate that you can just leave it in the join. You cannot even optimize it that way. And therefore, I realized that when we were actually designing tables for VoltDB, some of the hacks that you almost automatically tend to do with VoltDB don't make any sense, and you can just leave it as it is. And what results is a cleaner interface between the a cleaner separation of concerns between your application, so to say, and the database. Now, with CAP, I mentioned that Stonebreaker argues it can be very misleading because certain kind of catastrophical events are not so relevant anymore. Networks are now highly consistent. And also Brewer came back to CAP in 2012 and restated some of his earlier proposals about the distributed choice you have to make, which in CAP means you have usually decide that you only take 2 out of 3. With ACID, that is something that I think was, for me, the most important thing to really look deeper into VoltDB when I realized that much of what I can find in other products is base or eventual consistency. And that has a lot to do with your problem domain. If your problem that you have to solve has some shape like double bookkeeping, you probably need ACID. And something that does not usually have that is, for example, if you're serving websites or just tracking individual users. They don't have anything to do with each other. They have no real interchange, maybe for a certain constellation of a website. And then you have total parallelity, so to say, if data is completely separate. And you might not need ACID, in fact. And if somebody does something strange with his own shopping cart and just fires lots of commands from separate browsers that are all open on his account, you don't care. Then he just might lose some books that are in his shopping cart because he's just playing around. But coming back to games again, if you have something where one player is giving another player something, and you cannot have the situation that all of a sudden that sword that the one player gives the other player exists twice in your system or is getting lost, or they have bought virtual items that can also not be duplicated by an error in the software, or shouldn't at least, then you have something like double bookkeeping. And if you have that requirement, then what you need is really ACID. And that's really hard to emulate with a database that does eventual consistency. So that, for me, was definitely a point where VoltDB became so much more attractive. What is really going on? How can VoltDB do this? What I'm just introducing here as features. So looking at 4 different main architectural decisions they made. First of all, as I said, VoltDB is horizontally partitioning the data. That means the tables are stored on individually different machines, and they are simply hashed on their primary key, so that one entry goes on that server, one other entry goes on that machine, another entry goes on that machine. And that is also used for what they call case safety. That's replication of the data, so that it doesn't only go here, but there's a replica also going there, so that if that server goes down, there's also a separate copy on another server. What they are using for making it work to have tables being horizontally divided is the fact that many real use cases turn out to be Snowflake structures in the data. If you take a simple example, if you have customers and those customers have addresses and orders, and invoices and co-workers, you always have the primary key of the customer in the center of the snowflake. And the snowflake can branch out, and you can have other items of orders that are then again dependent, so to say, on that one customer. But in the end, they're all really sensibly grouped to that one customer, so that a central PK has to be identified. And then you design your entire database in a way that you say, okay, everything that belongs to that snowflake should end up on the same server. And then there's some data that is not really part of that snowflake. For example, it could be your products, because they're, so to say, in a different dimension. They are not dependent on the PK of the customer. And you have maybe 100 or 1,000,000 products that live on different tables that cannot be grouped to that snowflake. And that's fine. And what happens then is that VoltDB partitions everything it can, everything that is dependent on that main primary key, into the individual machines using a hash. And the data that is not part of the snowflake is replicated across every server. And the beauty of that is that if you think it through, very often in real examples, something, for example, like the product numbers or the product entries in a database, it makes a lot of sense to replicate them across all servers, because they are usually changing very infrequently compared to customer data or order data. And when they change, VoltDB takes over the job to synchronize the change across all individual servers. That's completely transparent. That architecture allows it to make transactions on individual snowflakes, usually within one machine. And that's really the goal. If you have a horizontally partitioned database, what you want to achieve is that you can complete an entire transaction on one machine. Another way that VoltDB achieves very high speed is using baked-in stored procedures. And for that, VoltDB, I am tending to say, unfortunately, uses Java. So a stored procedure in VoltDB is something that's not quite as cheap as, for example, MySQL, but you have to wrap it in a little bit of Java. This is all. It's not very much. It's also pretty simple. And the reason's obvious. I mean, in the end, they are using these procedures and compiling them into the server. You can also shoot ad hoc queries and bypass this, but to really have high speed and high velocity, you would have to be able to know what queries you will need and formulate them like this in a Java class and then compile them into the server. What you have then is a server that ideally has baked in very fast native transactions, so to say, and executes them in a single thread, having ideally all data that it needs available on one machine. And that is something that is a usual Erlang technique, I would say, that if you have a resource that is potentially the victim of a race, you usually use one process to use it as a funnel to govern that resource, and every other process has to go through that process to be able to access it. And that's very much the same philosophy that VoltDB uses here, where they have one thread per partition, and they try to separate the workload in a way that on each individual transaction, it's one thread that is doing the entire transaction in one go. And that's very, very different from what's going on in usual SQLs that are created to have one thread, or to have one transaction being executed with yielding to other transactions in the meantime, and then coming back, continuing the execution because it might have to wait for the hard disk to respond, or there's some other reason that it first has to gather all the data that it needs to complete. And that's one of the main differences where VoltDB has been designed in a way that's absolutely different from what was there before. And what they can do through that is throwing away, as they say, 75% of what a usual DBM usually does, because they are putting away with locking and latching and buffer management, and they just stay with that paradigm that they try to share, that they try to intelligently share the work on the individual machines in a way that they can be executed in one. So that was another stick figure. I discovered these, and I didn't really understand how to change the figures. So I started to combine stick figures and XKCD style, so to say, with dinosaur comics. And that was one result here. And actually, it's when I asked Joe Armstrong if he would review Erlvolt, he said, yeah, you can do that. And then a little later, I came back and he was like, oh, I got sidetracked. Sorry. I programmed on my time management program. So I sent that to Ryan too, and he didn't think it was funny. So I have a question. Who here has programmed his own time management program? Just nobody? No. That's funny. So Ryan said it's not funny because everybody does that. So using VoltDB with Erlang, this is how it looks. If you call a procedure, in this case, that insert there is not the SQL insert, but it's the Java class insert for this example. It's just to be very clear here. It's not that you write SQL there in parentheses, but you call Java classes that you have programmed, as I earlier showed, this select class. But nevertheless, what happens then on the Erlang side is just this. It's very, very short, and this is a complete example where you initiate the connection to the database, then you call a stored procedure. In this case, it's called select in the middle there, and then you get the table and you get a row and you get a string out of that row. There's no concept of having streamed results because in OLTP you usually have very short writes and very short reads. And in the end, this type of very short writes and reads is also what I use for a benchmark that I will come to in a minute. If you look at VoltDB, if you look at Erlvolt, you'll find more examples in the examples folder, and you find the benchmark source in the bench Erl in the bench directory. So at a certain point, I did a benchmark, trying to find out how fast this driver is. The driver is native. There's no C in it, and I had earlier done a benchmark for Node.js that is in part has been programmed in C. So I was very excited to see that the Erlang driver is actually as fast as the Node.js driver. And I can only guess, but I think that probably the very nice syntax that Erlang offers and bit parsing and protocol parsing, which is a lot what a driver actually does. It's bits and bytes, highly compressed, coming from the server, going to the server, that Erlang is very good at optimizing that, and it can actually be even faster than what you do with C. So the benchmark itself is using a staple of VoltDB that is in almost every benchmark they are using, and it's a TV contest voter example. The idea is you have millions of callers. They're all calling in at the same time in a very small time window. There's a very small set of candidates that they can vote on. And essentially, you just have to make sure that everybody just votes once and doesn't phone in a dozen times. And every caller can, of course, be identified by his telephone number. So I tried that using Amazon EC2 cluster instances. That makes it something that everybody can pretty much try out himself. In this case, my result was 877 transactions per second, because those transactions are even 4 or even 6 operations, depending on how you count it. that makes 3.5 operations per second in a way. The more interesting number in this case is maybe that I had 26,500 transactions per second per CPU core, as this gives you some idea how much hardware you might need for a given task. It was pretty nice to see that Erlang, of course, kept stable under overload even. Things didn't crash. And when the overload was diminished again, it just kept going. For this benchmark, these are the tables. Pretty simple. You have a contestant that is who you can vote for. You have the individual votes. They are identified by their phone number. And then you have area codes for individual states to make it a little more interesting, and add another lookup to show how fast VoltDB really is. The 4 operations that you have are this. Every transaction, so to say every vote, goes through these 4 things. You look at the consistent number, you see if it's a valid number, then you look at whether it has already voted, this telephone number has already voted before. Then you check the area code that the voter comes from, and if everything is okay, then you record a vote. The SQL statements that VoltDB offers are not the entire SQL range. They are the usual suspects, so to say. You can delete, you can insert, you can select, you can update. You can create indexes, tables, and views, which is quite interesting because, for example, that benchmark was using a materialized view to be able to have immediate results, so that whenever you wrote, a materialized view was updated immediately, so you always could query the status. The SQL functions that you can use in VoltDB are like this. What is missing, and it's quite clear why, are ranges in where queries, because of the way that you have to go across the entire cluster, so to say, to find ranges. That's something that VoltDB is not good at. Then VoltDB adds extensions to SQL, and they are for creating procedures, and they are for managing the partitions to make procedures local to a partition or using multiple partitions, and the same is true for tables. So wrapping up, here are resources. This slide is going to be, these slides will be on the internet, hopefully in a format that your computer will be able to read. You have here the downloads where you can find Erlvolt itself, VoltDB, and also a more detailed description about the benchmark where you have pretty much everything you need to try it yourself. There are also more examples, and there's the file that I quoted earlier about the philosophy that originally kicked off the development of VoltDB. If you have any questions, I'll be happy to take them now, but also don't hesitate to write to me, please, and follow me on Twitter. I'll be talking more about what we are using for this, which is the game server stack, which is quite interesting constellation, also using Lua to program the game logic in. And VoltDB has a forum that's worth checking out. If you try stuff, the VoltDB guys are really, really nice, really cool. Check out the forum and ask you questions there if you would like to. So, are there any questions? Please.
What's the deployment story like as far as ease of deployment and management of like cluster?
Sorry, can you speak up?
What's the deployment like as far as like ease of management of managing and deploying a cluster?
I still can't hear you. Sorry.
Like deploying these servers, running a cluster. How does that compare to trying to like run MySQL?
Do you have a microphone for the question? No? So maybe just come up, please.
I'll come up afterwards.
Very cool, thanks. Thank you.
I was just wondering if you could speak to like deploying this and running and managing a cluster as far as ease of use compared to running MySQL or Postgres.
Right. It's not as easy to use as MySQL. You have to do some planning because you have to identify which is your main primary key, how is your Snowflake actually looking. It doesn't take very long though, and it's also quite informative. It's quite interesting because you understand your data better, and it helps your abstraction. As I said, what we found, it's even cleaning up your design at some point I found it's almost a habit that you start to optimize stuff even before you write it down cleanly in database design. So then you have to write those wrappers in Java, which you have to do. VoltDB is offering a tool, though, that you can translate existing MySQL tables to VoltDB tables. I have never tried that, I have to say. But they're obviously working there. They also have a command line tool that's very much working like the MySQL command line tool to be able to access your data and play around with it. And initially, VoltDB was very inflexible how you could access your data. But meanwhile, they have understood that customers wanted to be agile and be able to shoot queries with whatever comes to mind, which in my view is very important, especially when you're developing. Thanks. Other questions? Anything comes to mind? Sure.
So if the database is in memory, right, how the durability property of basic is satisfied in this case?
I heard the first part and not the second.
So if the database is in memory, right, how the durability property is satisfied?
There are multiple steps there. I would like to. Well, initially, VoltDB, the guys insisted to be in memory and that's it. You know, like Google is in memory, basically. So they never store their stuff. It's replicated. If a server goes down, there's another replication there, so you don't have to store it on disk. And people really didn't like that. And I think it's also, for developing, it's really hard to use. Then, I believe they were lucky, because they discovered that this rhythmic scheduling of the transactions that I mentioned earlier always gave them a time gap that was excellently suited for writing away the current memory on disk. So they found that they had created a time window there that they had to use at any rate for the scheduler. That was just excellent to create disk persistence. And then they worked on that to the point that now, what I understand, it's 100% disk persistent. And you can, of course, you have to have the right disk controllers that really give you the OK only after it's persistent. And it does cost you a little bit of velocity if you insist on having that OK back instead of just the OK that it is stored in memory. But essentially, the trick is that there is this gap at any rate, and they use that to write stuff to disk. And that's why it can be incredibly fast and still disk persistent.
But is there a way on the client side to specify that I'm interested in the success response only after the data is reliably persisted on disk?
Yes, there is. You can switch that. More questions? I'll be happy to answer them. Okay, yeah.
So once you've gone through the exercise of figuring out your Snowflake and laying out your cluster and whatnot, then over time you're going to want to perhaps scale that up or grow it as you're loading. So how does that happen? You just add nodes live, but it seemed like it would be easily to that.
You mean the part where your data structure evolves, or where you add more hardware?
I was thinking the second, but the first is an interesting question also, so we'll take both.
Okay, so I start with your question, the hardware. With VoltDB 4, now you can add servers on the fly. That means that the hashing is not quite as simple anymore as it was. It used to be a real static hash, and that's it, which was quite elegant. That doesn't work for elastic scaling, so that has become a little more sophisticated there. But now you can add hardware on the fly. And answering the first, this thing with the snowflakes, and it's parallel to another fact that it seems that people found that real data, like real warehousing data, is in the area of 2 gigabytes as a magnitude. That means that since some time now, and only since some time, but we are now at a point where all data can be kept in RAM. And that was not so before, because the requirements of actual business didn't really change so much during the last, like the essence of what's happening on the business side didn't really change as much as hardware capabilities increased. And with a Snowflake, it's a similar thing. That's not maybe something that comes up first if you think about your data structure, but even if your data evolves, as I said, there's always data that's not part of the Snowflake, but the likeliness that it is in the Snowflake is probably very high. And the likeliness that your business all of a sudden does not have the customer as main Snowflake primary key anymore is pretty low.
Thanks.
Thank you. Any more questions? I'll be happy to hear them. Okay, please use my email address, mail me directly if you're interested, if you checked stuff out, if you got stuck. Also use the forum. I'll be happy to hear from you. Thank you very much.